Hi all, this is lecture 23. We are working our way towards the end of the semester here, and we've got a section 11.4. 11.4 is all about comparison tests. We're going to talk about two different comparison tests today, and then we'll talk about which one we like better. So first of all, let's consider this series here on the left. We have the series n equals 1 to infinity, 1 over 2 to the n plus 1. And that's not geometric, right, because of the plus 1. But it looks a lot like a geometric series. And what we want to do is talk about can we use the fact that it's almost a geometric series to determine what's going to happen, okay? Now, if we compare these two series, on the left, I'm adding 1 to the denominator compared to the right, and that's going to make my fraction smaller. So what I can say here is I can say that, I can say that 1 over 2 to the n is, let's see, if I'm adding 1 to the denominator, that makes my fraction smaller. So this one is bigger than 1 over 2 to the n plus 1, right? And we can show that if we needed to. We could multiply both sides by both denominators, and we'd have 2n plus 1 is bigger than 2n, and that makes sense. Okay, so we know that this is true. And so then what we want to say is, what do we know about the other series? What do we know about the series summation n equals 1 to infinity of 1 over n plus 1? What do we know about that one? So we know that that one is smaller, but what do we know about the one in blue? The one in blue is geometric. So now what we can say here is that if this is true for the fractions or for the sequences, then their series must also, that must be true for. My series is greater than this. Summation n equals 1 to infinity of 1 over 2 to the n plus 1. And so if I can show that this one here converges to a specific number, then this one is equal to a number, and my series is less than that, and therefore it must also be equal to a number. So what we can say is we can take the one in green and say, okay, let's look at the summation n equals 1 to infinity of 1 over 2 to the n. And this is geometric, so let me find its sum. Well, in order to find its sum, if it's geometric, I need to talk about I need to make it look like a times r to the n minus 1. And I have something to the n. So the first thing I want to do is I'm going to make this all one fraction to the n. And I can do that because 1 to the n is just 1. And then I want it to be n minus 1, so I'm going to pull one of those to the front. So n equals 1 to infinity, pull one out front, and then the rest of them will be n minus 1. I had n, I moved one away, now I have n minus 1. And then this is my a, and this is my r. And therefore, this series is equal to a over 1 minus r. And that's equal to 1/2 over 1 minus 1/2. And that's 1/2 over 1/2, which is equal to 1. So now I know that that series is equal to 1, and so now I can say, okay, well, this one's equal to 1. And if I flip this around, what I actually have is I can say that sum n equals 1 to infinity of 1 over 2n plus 1 is less than 1, and therefore it must converge. Okay, because the sum is less than a specific particular number. And therefore it must converge. And the formal way we say that is that this is the comparison test. Okay, so if we have two series with positive terms, then if the second one is convergent and my series is less than or equal to that one for all n, then my series is also convergent. Okay. If the second series is divergent and my series is bigger than that for all n, then my series is divergent. Now, why might this be true? Well, what we can do is we can look at some pictures. So let's think about 4 separate pictures here. Let's look at a coordinate plane. Now we know what our values are positive, and we know that they're going to have to increase because you're adding positive numbers. So the numbers are going to go up. But we want to know is there an L value that they approach? So here's my L value, my limit. Okay. And so let's suppose that, let's stick with what we had up here. So the series that I know about is blue, and the series that I don't know about is yellow. So let's go with BN is the blue one, the one that I know things about. And I'm going to go orange because it's a little bit darker. AN is the one I want to know about, okay? So if you think about BN, BN is a series that we know because let's suppose it converges. So if it converges, let's say it goes to L over time, okay? Now, so BN goes to L. It converges. If my AN is less than that for all N, so it's got to be somewhere down in here, then we could also say that AN is less than or equal to BN for all N, then AN also converges, right? Because it's got to be below, right? It can't go above my L line, so it's got to converge to something at least, at most L, okay? Now, is that true if I do the same thing but make it increasing? So if this is my plot, and we're going to make the same thing we did up here. So here's my L. And now we're going to use that BN still goes to L. So BN. But now my N is greater than or equal to that BN. So it's somewhere up in here. Can I still say that it converges? No, because it's above my blue line that converges. So I don't know how far above. Maybe it squeaks in there, maybe it doesn't, but likely it doesn't. Okay, in this case, your AN, we don't know. Okay, it likely diverges, but we're not sure. Okay, maybe it's close enough to BN that it works. Third case, what happens if we have the same setup, only this time BN diverges. So let's let BN diverge. And that means it's going off to infinity. Okay, so BN goes to infinity. Therefore, if my series AN is greater than or equal to BN for all N values, that means it's up here. Well, if BN is going to infinity, then AN must be going to infinity as well. So, and this is the series, by the way. So then the series diverges as well. Okay, so that's the second part. So the top two here are true. And then the other case that we could have, what happens if, and I don't need the L this time, if BN converges. Oh, sorry, no, I still want BN diverging. If BN diverges, so BN's going off to infinity. So BN diverges. And I now have AN is less than or equal to BN. So it's somewhere down in here. Does it diverge or does it converge to something in here? We just don't know. So that's why we have to be particular. We have to say, okay, either BN converges and I'm below it, or BN diverges and I'm above it. Otherwise, I can't say anything. Okay. And so let's look at an example in each case. All right, so let's think about what we want to compare to. So let's consider this first one, series n equals 1 to infinity of 5 over 2n squared plus 4n plus 3. And typically when you're going to compare things, you're essentially going to take off this part of the denominator. Okay, so we're going to compare to the sum n equals 1 to infinity of 5 over 2n squared. Because we actually know what happens with this one, right? So if I pull the 5 and the 2 out front, so this is 5 over 2, times sum n equals 1 to infinity of 1 over n squared. All right, now, from the last section, we know that this is a p-series. And its n is greater than, sorry, it's p, not its n, its p value is greater than 1, which means that it's convergent. If If you want to show that, you could use the integral test to integrate that. You're going to get negative 1 over n. N goes to infinity whenever negative 1 over n. Negative 1 over infinity goes to 0, so it converges. So that's what we're going to compare it to. So in order to show that ours also converges, we need to show that this is less than. Okay, so can we state that? Well, we have 5. We're going to say that 5 over 2n squared plus 4n plus 3 is less than 5 over 2n squared. If this is true, then it's less than my bn, and my bn converges, so the an will converge. Okay. We can do this by multiplying both sides together. So this is going to give you 10n squared less than 10n squared plus 20n plus 15. And you can subtract the 10n from n squared from both sides, and you get 20n plus 5 is greater than 0. N is positive, so this is always true. And so therefore, by comparison test, the sum n equals 1 to infinity of 5 over 2n squared plus 4n plus 3 converges. Okay, but notice what I had to say. In order to say that, I had to say, here's a series that I want to compare it to. This series is convergent, and my series is less than that convergent series. Okay, so that's one option. In example 2, keep in mind here, they put some restrictions on this one. You're going n equals 1 to infinity, but you're only talking about n greater than or equal to 3. And when natural log of n is greater than 1. Okay, you know that natural log of n should be greater than 1. It is for all n values that are larger than 1. And so if we're letting n be greater than or equal to 1 or 3, you know that that's positive. Okay, so what do we want to do? We want to compare this. So we want to compare to, if I were to take away the ln, this would be 1 over n. So what looks like ln n over n? Just the harmonic series. So we're going to compare to n equals 1 to infinity of 1 over n, which diverges. We know that because it's the harmonic series. Okay. Now, all we have to show then is that my series, the ln n over n, is greater than this one. So we want to state that ln of n over n is greater than 1 over n for all n greater than 3. And so if we multiply both sides by n, this is the ln of n is greater than 1, and that's true when n is greater than or equal to 1. So that's true for us. And so ours is larger than something that diverges, and therefore, by comparison test, the sum n equals 1 to infinity of ln of n over n diverges. Again, that's one that we were able to do also by integral test, so you can kind of verify that way. Okay. Now, this one's comparison test is not my favorite, mostly because you have to make sure you have the right series that you're comparing it to, and you have to have the right relationship, and it's harder to think about. What's always better is the limit comparison test. And this says that if I have two series and I take the limit of the two sequences, and that's equal to a constant, as long as that constant is a number and greater than 0, then those series are going to do the same thing. They're either going to both converge or they're going to both diverge. And that way you don't have to worry about which one's larger or smaller. So limit comparison test is always better than the comparison test, if you can make it work. Okay. Sometimes there are cases where comparison test is better, but almost always limit comparison test is going to win. Okay. So when in doubt, use limit comparison test. Okay. So here we go. We want to know whether this series converges or diverges. So 1 over 3n minus 1. Well, 1 over 3n, we want to compare it to this one. So let me make that a different color. We're going to compare to n equal 1 to infinity. If we take away that minus 1 in the bottom, it's 1 over 3 to the n. Okay. So this series here is geometric. And if we set it up properly, we would factor out the 1/3. And make it 1 over 3 to the n minus 1. And then this is r equals 1/3. And so this is geometric. Whoa, sorry, friends. Things are popping up on my iPad. In this case, our r is equal to 1/3, and geometric series converges when your r, absolute value, is less than 1. And so because 1/3 is less than 1, then this one converges. So that's great. I know of a series that looks similar that converges. So if I wanted to use a comparison test, I'd have to show that my series is smaller than this series. But look what I've done. I've subtracted 1 in the denominator, and that makes it bigger in the denominator, just slightly bigger. So I can't use comparison test, but I can use limit comparison test. So limit comparison test in limit comparison test, I want to look at the limit as n goes to infinity of, and to be honest, it doesn't matter what our c is, and therefore it doesn't matter which one goes top and bottom. Okay, it's up to you which one goes top and bottom. So I'm going to put the 1 over 3 to the n on top, and actually let's go 3n minus 1 on top, and 1 over 3 to the n on the bottom. So I want to look at this limit. Okay, so if I do that, then we go n goes to infinity, and we want to fix this, so we make it 3 to the n over 3 to the n minus 1. Oh, actually, I might want it the other way. Yeah, let's do it the other way. It's just easier to see if we do it the other way. So sometimes if you can't see it or do the algebra, flip it over. So 1 over 3 to the n over 1 over 3 to the n minus 1. And so if you flip these over, that's 1 over 3 to the n times 3 to the n minus 1 over 1. And that's the limit as n goes to infinity of 3 to the n minus 1 over 3 to the n. And what we can do here is we can split this. So this is the limit as n goes to infinity of 3 to the n over 3 to the n minus 1 over 3 to the n. And for in terms of limits, this is the limit as n goes to infinity of 1 minus 1 over 3 to the n. And then when you take n goes to infinity, this is 1 minus 1 over infinity, and that turns out to be 1. And so therefore you get a number that is non-zero. Okay, so look at our up here, our c, where c is finite and greater than 0, then they both either converge or diverge. So because the limit here is a number greater than 0, then this one does what the other one does. So this one converges because the other one converges by limit comparison test. Okay, so that's how limit comparison test works. Again, 9 times out of 10, you're going with limit comparison test.